complex ideas. We pull out the essential bits and hopefully give you that satisfying aha moment.
Hope so.
Today we're plunging into one of physics' really profound, almost unbelievable problems.
Yeah.
You see, modern physics, it stands on these two colossal pillars. General relativity, describing the huge cosmos and quantum mechanics, which totally rules the subatomic world.
And both are just fantastically successful, I mean, in their own areas.
Exactly. But here's the kicker. They fundamentally clash. It's like having two super detailed maps of London, but one's written in, I don't know, ancient Greek, and the other in binary code.
That's a good way to put it. And that clash, that deep conceptual divide, it really shows up when you look at the universe's extremes.
Like the Big Bang, or inside a black hole.
Precisely. Places where both theories should work, but they just,
Yeah.
well, they break down. They give nonsense answers.
And this incredible quest, the search to bridge that divide, to find that one unified theory, it often leads physicists to this hypothetical particle, a theoretically necessary one, they say, the graviton.
That's the one.
So our deep dive today is all about understanding, why do we think we need this particle? What should it actually look like based on theory? What are the huge challenges in finding it?
And the theory's trying to solve it all.
Yeah.
Some wild ideas out
Oh,
there.
yeah, like string theory and loop quantum gravity. We'll get into those. The goal is really to give you a shortcut, a way to kind of grasp one of the deepest mysteries in physics today.
Okay, let's do it. Where should we start? The cosmic divide itself.
Yeah, let's unpack that. Why is gravity such a quantum quandary? Let's start with
Yeah.
big picture, general relativity.
Right. Einstein's masterpiece from 1916. It totally flipped our understanding of gravity on its head.
Yeah, before Einstein, it was Newton's idea, right? Gravity as this mysterious force pulling things together.
Exactly. But Einstein said, no, gravity isn't a force in the usual sense. It's actually the curvature of space-time itself. Mass and energy warp space-time, and objects just follow these curves.
That's what we feel as gravity, just following the contours of space-time.
Precisely. And its track record is, well, stunning.
Absolutely staggering, yeah. I mean, predicting Mercury's wonky orbit perfectly, seeing starlight bend around the sun, that's gravitational lensing.
Time dilation, too. Time literally runs differently depending on gravity.
And then the big one recently, well, relatively recently, LIGO and Virgo directly detecting gravitational waves, those ripples in space-time itself.
Monumental. Direct proof from merging black holes, neutron stars, confirming GR in a completely new way back in 2015.
Okay, so that's the macro world. Now let's shrink down, way down, to the quantum realm.
Right, so here we have quantum mechanics, and more specifically quantum field theory, or QFT. This is the language of the very small.
And in QFT, forces work totally differently, don't they? No smooth fields, it's all particles.
Exactly. Forces arise from the exchange of discrete packets of energy tiny particles called force-carrying bosons. It's like playing catch. You throw a ball, you exert a force.
So for electromagnetism, that ball is the photon.
Correct. For the strong nuclear force holding atomic nuclei together, it's the gluon.
And the weak force, responsible for radioactive decay.
That's mediated by the W and Z bosons. This particle exchange picture is the heart of the standard model of particle physics, and it's been unbelievably successful at describing those three forces.
Okay, so we've got GR for the big stuff, QFT for the small stuff. Both work brilliantly. Where's the clash?
Here's the fundamental problem, the incompatibility. General relativity is classical. It's smooth, deterministic. It tells you exactly where things are going.
No probabilities, just certainty.
Right. But QFT is inherently probabilistic. It deals in uncertainties, wave functions, probabilities, and crucially, it usually assumes a fixed, flat space-time background to operate on.
But GR says space-time isn't fixed. It's dynamic. It bends and curves.
Exactly. That conceptual chasm becomes a practical disaster. At the extremes we mentioned, the Big Bang singularity, the center of a black hole.
Places where gravity is incredibly strong and things are happening on tiny scales.
Right. Both theories should apply there, but when you try to combine them mathematically, they just break. They spit out infinities, meaningless answers.
Nonsense numbers.
Pretty much. There's a fundamental energy scale, the Planck scale, where quantum gravity effects must be important, and that's where our two best theories just fail to talk to each other.
Right.
It's, genuinely one of the deepest unsolved problems we have.
So the most obvious path forward, or at least the most straightforward sounding one, is, well, if the other three forces have quantum messenger particles.
Why not gravity?
Exactly. Maybe gravity also has a quantum mediator. and that's the graviton hypothesis.
It suggests gravity is also carried by a quantum particle, the graviton, exchanged between things that have mass or energy.
And those gravitational waves we detected, in this picture, they'd be what? A huge flood of these gravitons?
The coherent state, yeah.
Yeah.
A synchronized wave made of a vast, vast number of gravitons all moving together.
Interesting. And the name graviton, where did that come from?
It actually dates back quite a ways to 1934. Soviet physicists Dmitry Bolkintsev and Fyodor Gelprin coined it.
Wow, 1934. So people were already thinking along these lines.
They were. And this quest, the hunt for the graviton, it's not just, ticking another particle off the list. It's fundamental. It tests whether quantum principles are truly universal.
Does quantum mechanics apply to everything, even the fabric of space-time described by GR?
That's the core question. It forces us to really confront what space and time are, what reality is at its deepest level.
Okay, so if this graviton exists, what would it be like? What's on its hypothetical ID card? These properties aren't just pulled out of thin air, right? They come from the theories themselves.
Absolutely. They're constrained by what we know about gravity and quantum mechanics. Let's start with the basics. Mass, speed, range.
Okay. Gravity reaches across the entire universe, right? Infinite range, like electromagnetism.
Correct. And for a force to have infinite range, its carrier particle generally needs to be massless, just like the photon for electromagnetism.
And do we have evidence for that?
We do. The fact that gravitational waves travel at the speed of light is really strong evidence. According to special relativity, only massless things can travel at the speed of light.
Makes sense. But physicists always like to check, don't they? Have they tried to measure if it has even a tiny mass?
Oh, absolutely. Experiments using Virgo data, observations of gravitational lensing, even tracking spacecraft like the Cassini mission to Saturn. They've put incredibly tight upper limits on any possible graviton mass.
So basically, as far as we can tell, it looks massless.
The limits are so small, they're practically consistent with zero mass. If it had even a tiny mass, its Compton wavelength would be enormous, like light years across, but the force would eventually drop off faster than we observe.
Are there theories that do propose a massive graviton?
There's some speculation. People have wondered if a tiny mass could maybe explain things like the weird rotation of galaxies, the thing we usually attribute to dark matter. But honestly, these massive graviton theories are theoretically very difficult. They often lead to instabilities, things that suggest the universe shouldn't be stable if they were true, like Ostrogowski's theorem points out issues.
Okay, so massless seems the safe bet. Now, what about spin? This is apparently a really key property. You hear spin 2 all the time with the graviton. Why spin 2?
Right, this is probably its most defining characteristic. It's deeply connected to the nature of gravity's source in general relativity.
How so?
Well, the spin of a force carrier is linked to the, let's say, mathematical shape or structure of the thing that creates the force field.
Okay, like for electromagnetism?
The source is electric charge. That's
Yeah.
just a number, a scalar, or you can think of the current as a direction, a vector, or rank 1 tensor, mathematically. And its force carrier, the photon, has spin 1.
Got it. So gravity's source must be more complex.
Much more complex. In GR, the source isn't just mass or energy density, it's the stress energy tensor. This is a more complicated object, a symmetric rank 2 tensor.
Whoa, okay. Rank 2 tensor. What does that actually mean?
It means it captures more information, not just how much stuff is there, energy
Yeah.
mass, but also how it's moving, momentum, how it's pushing and pulling internally, pressure, stress. It's a whole matrix of information.
So because gravity responds to this complex rank 2 source.
Its quantum messenger particle, the graviton, must have spin 2. It's a direct mathematical consequence. The spin reflects the rank of the source tensor.
And what does spin 2 do physically? Does it explain anything about gravity?
It explains why gravity is always attractive. Think about it. Spin 1 particles, like the photon, can mediate both attraction, opposite charges, and repulsion, like charges. But a spin 2 particle exchange only results in attraction between, like, sources of energy momentum.
Which is exactly what gravity does. It always pulls things together.
Precisely. There's also a really profound argument by Steven Weinberg, sometimes called the bootstrapping or uniqueness argument.
What's that?
He showed that if you try to build any consistent interacting quantum theory of a massless spin 2 particle, it inevitably, at low energies, has to look just like general relativity.
Wow. So if the graviton exists and is massless spin 2, then GR basically just has to be the right description of gravity at large scales.
It's like GR is unavoidable if you start from those quantum premises. It beautifully connects the particle view back to Einstein's geometric view. It makes GR feel almost inevitable.
That's amazing. Okay, any other key properties? Charge, antiparticle.
It's expected to be electrically neutral. And like the photon, it should be its own antiparticle.
So no antigravitons causing antigravity.
Not in this standard picture, no.
Yeah.
That idea is pretty speculative and doesn't really fit.
Yeah.
And maybe most importantly, universal coupling.
What does that mean?
It couples to the stress-energy tensor. Since everything has energy, momentum, matter, light, even gravitons themselves, the graviton interacts with everything.
Ah, so gravity affects everything and even affects itself.
Exactly. It's the only truly universal force. And that self-interaction, gravitons interacting with other gravitons, is the ultimate source of GR's nonlinear complexity. It's why the equations are so hard to solve.
And maybe why it's hard to quantize, which brings us to the big problem. If the graviton fits so neatly in theory, why is unifying gravity and quantum mechanics so hard? Why this non-renormalizability issue?
Right. This is the theory's Achilles heel when you try the standard quantization methods used for the other forces.
Okay, so explain renormalization simply. What are we trying to fix?
Okay, in QFT, when you calculate things like the probability of two particles interacting, you often use these things called Feynman diagrams. These diagrams include loops, which represent virtual particles.
Virtual particles, like particles that pop in and out of existence.
Sort of, yeah. Transient particle-antiparticle pairs allowed by the uncertainty principle. The trouble is, when you calculate the contributions of these loops, especially loops involving high energies or short distances, the math often blows up. You get infinite results.
Infinite probabilities. That doesn't sound good.
Not good at all. These are called untrivial divergences. Now, for the standard model forces electromagnetism, strong, weak physicists figured out a process called renormalization.
And that fixes the infinities. How?
Basically, yes. They found that all the different types of infinities that pop up can be systematically absorbed or canceled out by redefining just a few fundamental parameters of the theory, like the particle's mass and charge. You measure those parameters experimentally, plug them in, and voila, the infinities disappear, and the theory makes finite, testable predictions.
Okay, so renormalization works for the other forces. Why does gravity fail catastrophically, as you put it?
Because when you try to apply the same renormalization techniques to gravity, specifically calculations involving graviton loops, two or more loops, it goes haywire. You don't just get a few types of infinities you can absorb, you get an infinite number of different kinds of divergences.
And an infinite number.
Oh boy, yeah. To cancel out an infinite number of different infinities, you'd need to introduce an infinite number of new parameters into the theory, each needing to be measured experimentally.
Which is impossible. You can't measure infinite parameters.
Exactly. A theory that needs infinite measurements to make a prediction is useless. It has no predictive power. That's what we mean when we say general relativity is non-renormalizable using standard QFT methods.
So this failure isn't just a mathematical quirk. It's a huge clue, right? What's it telling us physically?
It's telling us that GR, as formulated, probably isn't the final story. It's likely what we call an effective field theory.
Meaning it works well in its domain, but it's an approximation of something deeper.
Precisely. It's valid at lower energies, far below the Planck scale. The infinities are a signal that the fundamental assumptions we're making, like particles being point-like or space-time being perfectly smooth at all scales, break down at those incredibly high energies or tiny distances.
So the failure points the way. It tells us we need a new theory, a more fundamental one that works at the Planck scale.
That's the interpretation. The non-renormalizability isn't just a problem, it's a signpost pointing towards new physics, towards a theory of quantum gravity.
And this has led physicists down some pretty fascinating paths. The two main contenders seem to be string theory and loop quantum gravity. Very different approaches, right?
Radically different, yes. Let's start with string theory. It offers this really elegant, if mind-bending resolution.
Its core idea is no more point particles. Everything's made of tiny vibrating strings.
That's the gist. The fundamental constituents aren't points, but unimaginably tiny, one-dimensional oscillating strings. Think Planck-length tiny 1035 meters.
And all the different particles we see, electrons, quarks, photons, everything, are just different ways these strings can vibrate, like notes on a violin.
Exactly like notes on a violin. Different vibrational modes correspond to different particles with different properties: mass, charge, spin.
Okay, so where does the graviton fit into this string symphony?
This is one of string theory's most celebrated results, maybe the most celebrated. It turns out that among the possible vibrational modes of a closed loop of string, there inevitably appears a mode corresponding to a massless particle with spin too.
Inevitably. It just pops out of the math.
It cops out automatically. You
Yeah.
don't put it in. The theory demands it. Its existence is a direct, unavoidable mathematical prediction.
That's incredible. Was it immediately recognized as the graviton?
Actually, a bit of a historical twist there. When string theory was first being developed, mainly to describe the strong force, this massless spin-2 particle was seen as a problem, a nuisance even,
Ha. A flaw turned out to be its greatest feature.
pretty much. They soon realized this flaw was the quantum of gravity, the graviton, and the theory was rebranded as a potential theory of everything, including quantum gravity.
And does string theory solve the renormalization problem, those pesky infinities?
It does in principle. Because strings aren't points, they're extended objects.
Hmm.
They interact over a small region, not at a single point. This smearing out of the interaction effectively smooths out the calculations and tames those ultraviolet divergences that plague point-particle theories of gravity.
And what about general relativity itself? Does it fit in?
Yes, in a really profound way.
Yeah.
For string theory to be mathematically consistent, the background spacetime on which the strings propagate must obey equations that, at low energies, look just like Einstein's equations of general relativity.
So GR isn't fundamental, but it emerges from string theory's consistency conditions.
Exactly. GR emerges as a low-energy effective description. It's baked into the mathematical fabric of string theory.
Okay, that's string theory. Now, what about loop quantum gravity, LQG? You said it's a stark contrast.
It really is. LQG takes a fundamentally different starting point. It takes GR's main lesson that spacetime isn't a fixed background, but a dynamic entity completely seriously from the outset.
So, unlike string theory, which often starts with strings moving on a background spacetime,
LQG tries to be background independent. It doesn't assume a pre-existing stage. It attempts to quantize spacetime itself.
quantize space and time, what does that even mean?
It means applying quantum rules directly to the geometry of spacetime using mathematical tools called Ashtekar variables, and the result is revolutionary. Spacetime itself becomes discrete at the Planck scale.
Discrete, like pixels on a screen. Space-time isn't smooth.
Not at the fundamental level, according to LQG. It's composed of indivisible quanta of geometry. Space has a minimum area, a minimum volume. It has an almost atomic structure.
Wow. And these quantum states of geometry are represented by things called spin networks.
Yes. Spin networks are graphs where nodes represent tiny chunks of quantum volume,
Wow.
and the links between them represent quantum areas connecting them.
And the evolution of these networks through time is a spin foam, like a quantum history of geometry.
You got it. It's like a higher dimensional version of Feynman diagrams, representing the evolving quantum structure of spacetime itself. Think John Wheeler's old idea of spacetime foam, but made mathematically precise.
Okay, so in this picture, where's the graviton? Is it fundamental like in string theory?
No, and this is a crucial difference. In LQG, the graviton is not fundamental. It's an emergent phenomenon.
Emergent, like how sound waves emerge from the collective vibration of air molecules.
Exactly like that. A graviton in LQG is seen as a collective excitation, a ripple, propagating through the underlying discrete quantum geometry, the spin network or spin foam. It's analogous to a phonon, which is a quantum of vibration in a crystal lattice. A phonon isn't a fundamental particle. It's a coordinated wiggle of many atoms.
So a graviton is like a quantized wiggle in the atoms of spacetime.
That's a good way to think about it. The smooth spacetime of GR and propagating gravitational waves made of gravitons are seen as large-scale, low-energy approximations of this fundamentally granular reality. The graviton becomes a secondary, derived concept.
That really highlights the core difference, doesn't it? String theory quantizes a particle, the string, whose vibrations include the graviton, often on a background. LQG quantizes the background spacetime itself, and the graviton emerges later.
Precisely. It's a fundamental disagreement about what needs to be quantized first.
Okay, let's switch gears to hunting this elusive particle, or maybe this emergent excitation. Detecting, it seems, well, incredibly hard.
Oh, it's arguably the most formidable detection challenge in all of physics. The reason is simple. Gravity is just unbelievably weak compared to the other forces.
So the chance of a single graviton actually interacting with any detector is tiny.
Astronomically small. Its interaction cross-section is minuscule.
I remember Freeman Dyson's famous thought experiments painting a picture of near impossibility. Didn't he calculate something like needing a detector the size of Jupiter near a neutron star just to catch one graviton every decade or so?
He did. And an Earth-sized detector looking for gravitons from the sun would have to wait billions of years for a single event. It made quantum gravity effects seem utterly beyond experimental reach, purely theoretical.
But that view has changed, hasn't it? There's been a sort of paradigm shift.
Absolutely. Two revolutions happened. First, the dawn of gravitational wave astronomy with LIGO and Virgo detecting those powerful waves in 2015.
Right, those waves aren't single gravitons, but huge floods of them.
Exactly. Up to 1036 gravitons in one burst from merging black holes. Second, we've seen incredible advances in quantum sensing technology building detectors sensitive to incredibly tiny energy deposits.
So the new strategy isn't to wait for a stray graviton, but to use these powerful gravitational waves like a beam of gravitons.
And try to see if that beam can kick a highly sensitive quantum detector here on Earth.
Precisely. That sounds much more doable. What's the specific idea?
The leading proposal revolves around something called the Gravito-phononic effect.
Analogous to the photoelectric effect, where a photon kicks out an electron.
Exactly. The idea is that a passing gravitational wave, this flood of gravitons, could deposit just a single quantum of its energy into a specially prepared massive detector. This energy deposit would excite a collective vibration in the detector material, a quantum of sound called a phonon.
So you're looking for one tiny ping of sound energy created by the wave.
A single phonon's worth of energy, yes. The proposal by Igor Pekovsky and others suggests using something like a 15-kilogram bar of beryllium, or maybe superfluid helium, cooled down to its absolute quantum ground state almost perfectly still.
And how do you know the ping came from the gravitational wave?
That's where LIGO and Virgo come in. They act as a herald. They detect the waves, tell us it's coming, where it's from, what its frequency is. You then look at your quantum detector at that exact moment for an energy jump, a single phonon excitation, precisely matching the gravitational wave's frequency.
That simultaneous frequency-matched detection would be strong evidence.
It would be incredibly powerful confirmation. Of course, the technological hurdles are immense. Cooling that much mass to near absolute zero and detecting a single phonon is, well, really, really hard. But potentially achievable in the coming decades.
Okay, but let's say they do it. They see a click in the detector perfectly correlated with a gravitational wave. Is that definitive proof the graviton exists and gravity is quantized?
Here's the crucial subtlety. It would be absolutely revolutionary, a Nobel Prize-worthy discovery, no doubt.
Yeah.
But it wouldn't on its own be definitive proof that the gravitational field itself is quantized.
Hey, why not if the detector clicks with one quantum of energy?
Because there's a potential loophole. The semi-classical alternative. Imagine the gravitational wave is purely classical, a smooth, continuous wave, as GR describes. But it interacts with the detector that is quantum mechanical.
Quantum detector can only absorb it in chunks, making it look like a quantum interaction.
Exactly. The discreteness could come solely from the detector's quantum nature, not necessarily from the gravitational wave itself being made of gravitons.
Okay, so what would be definitive proof then? How do you close that loophole?
You'd need to observe phenomena that a purely classical gravitational field simply cannot produce. Things that are uniquely quantum.
Like what?
The gold standard would be observing gravitationally mediated entanglement, using gravity to entangle two quantum systems, or detecting things like squeezed states of gravitons, which are purely quantum phenomena.
And those experiments are even harder?
Substantially harder, maybe even impossible with current or foreseeable technology. So the first step, detecting that single phonon click, is the focus right now. It wouldn't be the final word, but it would be the first piece of direct experimental evidence about quantum gravity effects, which would be incredible. It's really electrified the field.
Let's put the graviton in context a bit. How does it stack up against the other force carriers we know in the standard model?
The biggest difference, as we touched on, is spin. All the others, photon, gluon, WZ, are spin 1 vector bosons. The graviton is unique as a predicted spin 2 tensor boson.
And that reflects their sources, right? Spin 1 from vector sources like charge, spin 2 from the tensor source, the stress energy tensor.
Precisely. And that leads to gravity's universal attraction, whereas spin 1 forces can attract or repel.
What about their charges or how they couple?
Photons couple to electric charge, gluons to color charge, WZ to weak isospin-specific properties. The graviton couples to the stress energy tensor. Since everything has energy and momentum, its charge is universal. Everything feels gravity.
Including gravitons themselves, that self-coupling again.
Right, which makes GR nonlinear and hard to renormalize, unlike the other forces where the carriers, like photons, don't directly interact with themselves in the same fundamental way.
Okay, another comparison people often get confused about, the graviton versus the Higgs boson. They both relate to fundamental properties, mass and gravity, but they're different beasts. Right?
Very different beasts, yes. It's a common confusion, but important to clarify. The Higgs boson is a spin-zero scalar particle. Its field, the Higgs field, permeates space and gives intrinsic mass, basically inertia, to fundamental particles like electrons and quarks when they interact with it.
So the Higgs explains why particles have mass.
Exactly. The graviton, on the other hand, is the hypothetical spin-2 mediator of the gravitational force, the attractive force between objects that have energy and momentum, which includes mass.
So Higgs gives mass, graviton mediates gravity between things with energy mass.
You got it. There are distinct and complementary roles. You could theoretically have a universe with massive particles, but no gravity, or a universe with gravity acting on massless particles, like light. A complete theory probably needs both mechanisms.
Now, we focused on the graviton as this fundamental particle, or maybe an emergent one in LQG, but these aren't the only games in town for tackling quantum gravity or cosmic mysteries, are they?
Not at all. The challenges in quantizing gravity, plus mysteries like dark matter and dark energy, have spurred lots of alternative ideas. One broad category is modified gravity.
The idea here is that maybe GR isn't quite right on very large scales, and we don't actually need things like dark matter.
That's the motivation for some of them, yeah. Instead of missing stuff, maybe the law of gravity itself changes. Examples include things like FR gravity, which is a mathematical generalization of GR. These theories might still have a spin-2 graviton, but they could also introduce new particles, like a scalaron, or predict different types of gravitational waves.
And then there's MOND, modified Newtonian dynamics.
MOND is fascinating. It's less a fundamental theory and more a phenomenological rule. It basically says that below a certain very low acceleration threshold, like in the outskirts of galaxies, gravity just becomes stronger than Newton's or Einstein's theories predict.
And that explains why galaxies rotate faster than expected without needing dark matter.
It does, remarkably well in many cases. People are working on relativistic versions, like TVs, but the key point is these MOND-like ideas often don't rely on the standard picture of a fundamental graviton arising from QFT. Gravity just is different at low accelerations.
And then there are even more radical ideas. Emergent gravity.
Yeah, this is maybe the most profound shift in perspective. The idea here is that gravity isn't a fundamental force at all.
Not fundamental, like temperature isn't fundamental, it emerges from atoms moving.
Exactly that analogy. Gravity, and maybe even space-time itself, could be a macroscopic emergent phenomenon arising from a deeper underlying microscopic reality that might not even involve geometry or gravitons in the way we usually think.
What's an example?
The most talked about is probably Eric Verlinde's concept of entropic gravity. He proposed that gravity isn't a fundamental force, but an entropic force, something that arises from statistical effects, information, and quantum entanglement among some underlying microscopic degrees of freedom, maybe related to holographic ideas.
So in that view, the graviton just doesn't exist fundamentally.
It wouldn't exist as a fundamental force carrier? No. It might be a useful description of ripples in the emergent space-time, but not a basic building block. It's like asking for the particle of temperature or the particle of wetness. It might be a category error to even look for a fundamental graviton if gravity itself is emergent.
Wow. That really underscores that the graviton isn't a foregone conclusion, even if it's the most standard path.
Definitely not. These alternative and emergent ideas are really pushing the boundaries of how we think about space, time, and gravity.
So wrapping this all up, the graviton really sits at this fascinating crossroads. On one hand, it seems like this almost logical, theoretically robust consequence of trying to apply quantum rules to gravity as we know it via GR.
Yeah, the massless spin-2 properties fit beautifully.
But on the other hand, trying to actually do that quantization with standard methods leads to this brick wall of non-renormalizability, suggesting GR can't be the full story at the quantum level.
Exactly. And that tension fuels the major competing visions we discussed. String theory, where the graviton is fundamental, unavoidable part of the string's vibration.
Versus loop quantum gravity, where space-time is fundamentally granular, and the graviton is just an emergent ripple on that quantum geometry.
A fundamental particle versus an emergent excitation. It's a deep divide.
And for decades, this was all pure theory, wasn't it? Just math on blackboards. But now, things are changing.
They really are. The combination of detecting gravitational waves and the amazing progress in quantum sensor technology has opened up a completely new experimental window. These proposals to detect single graviton effects, like the Gravito-phononic effect, are incredibly ambitious, but they represent a plausible, maybe even near-term, path to actually testing quantum gravity ideas experimentally.
A shift from pure thought experiments to actual experiments.
It's huge. A successful detection, even that first step, click, correlated with a wave would be absolutely revolutionary. It would be the first piece of hard data in this field ever.
It would strongly suggest gravity does play by quantum rules ultimately.
It would. And while it wouldn't instantly tell us if string theory or LQG is right, or if maybe some emergent theory is correct, it would undoubtedly kickstart a whole new era of experimental quantum gravity research.
So really, this hunt for the graviton, it's so much more than just searching for another particle on a list.
Oh, absolutely. It's the focal point for this grand quest to reconcile the two pillars of modern physics relativity and quantum mechanics. It's about completing the picture of the fundamental forces of nature.
And whether we find it and find evidence that points towards emergence or something else entirely, the results promise to reshape our deepest understanding of space, time, and the very fabric of reality itself.
Couldn't have said it better myself. It's one of the biggest questions out there.
Definitely something profound to think about.